Windows because they have those all running Windows in that lab this term. Okay, so the slides that I'm showing you is based on an old sort of genesis of the core processor designs that was known as the Nehalem CPU. And it looked kind of like this, and it had these characteristics that it had all of these functional units, and it's superscalar, so it can have instructions that are going at the same time that are using these different functional units. That's what we mean by superscalar, right? You have multiple instructions in flight, they call it, right, at the same time. And so the book in chapter 5 uses the Haswell processor as its sort of poster child for the problems and the explanations in that chapter. And so the Haswell is this one right here, which is the successor to what Schofield is the Ivy Bridge. And I think the Haswell is not in hardly any way very much different from the Ivy Bridge. Slightly faster, I think, for the same clock rate. But anyway, I don't think we have an actual Haswell processor on any of our computers in our lab. We have Skylake and Kaby Lake, and the old Linux pool stuff is Sandy Bridge. Schofield is Ivy Bridge, but I don't think we have this exact one. Well, it doesn't matter. These are all so similar. You're not going to notice a whole lot of difference for the things that we're going to be doing on them. So the Haswell is the one they're using in your chapter, and the homework problems refer to the Haswell processor. And so this is the characteristics of the Haswell processor. And you notice that the difference between one of the differences between the Haswell and the original old ancient Nehalem processor is in the Nehalem processor, you have these functional units, and each of those functional units, that's the only thing that functional unit can do. And in the Haswell, it's a little different. You got 8 functional units, and these ones at the bottom, they just have one specific dedicated thing that they're capable of doing. But the 2 at the top are capable of doing different things depending upon what you ask it to do. So it can either do integer arithmetic or floating point multiplication or any of this other stuff, but it can only do one of those at a time in that functional unit. And so it's kind of like you have to think in terms of the interconnection between the components within the CPU. The registers are fed into the functional unit to operate on those registers and do something to those values in the register. So you have to have a data path going, physically into the functional unit and then out of the functional unit back into the registers. So they don't want to have all of these as separate things. They couldn't come up with enough data paths in and out, right? So they took this collection of functionality and they have one path in and one path out. But you get the flexibility of at any given point in time, it can be doing any of these different functions in that functional unit. And the same thing for 1, it can do arithmetic or floating point addition or integer multiplication or floating point multiplication. So if you wanted to do 2 floating point multiplications at the same time, you could use this one and that one. That would work. But if you were interested in doing a whole bunch of integer stuff at the same time, you could use this one for an integer and that one for an integer. And then this one down here is an integer and this other one is an integer. So you could get 4 integer arithmetic operations going at the same time through these different functional units. So you get a little more flexibility the way that's envisioned in the Haswell thing, as opposed to in the NALM, you get this floating point thing that it'll ever do. So you can't like use it to also do an integer thing. So you get two integers, one floating point multiply, one floating point add. So it's slightly different, you see, from the way they arranged this one. It's a little more flexible with the Haswell model. So this is the one that's used in your homework problems, this particular architecture of a CPU. And so that's the one that in table 512, that figure in your book that gives you the latencies for that particular processor. That's the one you should use in your homework. The latencies for the NALM older design that are in my slides here are shown as 4, 3, whatever, right? And the load in the store is shown here that says I could do one load and one store at the same time. Whereas in the Haswell, you'll notice you can do a load possibly with an address computation, that shift it left some bits and add it to the thing, that form of addressing mode. That's that address computation stuff. So you could do two loads. You got two things that can do loads and two things that can do stores, although only one of the stores can be doing an address computation associated with the store. So that's a little different from the NALM over here, where I only got one load, one store, right? So I can feed things into the processor faster with my Haswell design because I have more data paths coming out of the top level cache. We worry about caches in the next chapter. So it's a little more flexible, should outperform, obviously, this guy at a given clock rate. So what do we mean by these cycles? Well, if you want to do an integer multiply, the circuitry, when you take the two registers that you're pushing into the multiply circuitry, you have to pulse the circuit 3 clock pulses to get the result to pop out the other end of the multiply circuit, right? But what is this cycles per issue thing all about? Well, the way that these circuits work is they're pipelined. You think of it as a 3-stage multiply unit. And if I took register 1 and 2 and I pushed it into the multiply unit, after 1 clock pulse, that would be down in the second phase of the 3 phases, right? And this says that after 1 clock pulse, I can take another pair of operands, integer registers 3 and 4, some other registers, and I can push it into the circuitry for the multiply. That's called pipelining. So if I had 3 sets of 2 registers that I wanted to multiply together to get 3 products, right? I could pipeline them into this thing, and after 3 pulses, I get the first result. After the 4th pulse, I'd get the second result, and after the 5th pulse, I'd get the third result. So I got 3 results of multiplication in 5 cycles because I can pipeline in the very next clock cycle the other operands into the functional unit. So is there any questions about what we mean by pipelining? So this is another way that we make things go fast, in addition to having multiple functional units, which is what we refer to as a superscalar processor, where we can get multiple opcodes being executed using different functional units at the same time. We can also, in the functional units, pipeline things through them to get some overlap, right? Now, division is a weird beast because it's dependent upon the data, how many cycles it takes to complete it. You've seen this when you were doing your bit twiddling, where you had to deal with rounding and then, oh, well, if I rounded, maybe that rippled all the way across past the binary point and turned that thing into a 2, and then now I gotta change that and move it to the right, and then I gotta adjust this exponent to reflect that. So there's all these things that might happen that need to be dealt with as you're doing that kind of operation on these doing divisions, either in floating point or in um, integer, in fact. So that's why it shows a different number of cycles. It could take minimum of 11, as much as 21, and this is 10 to 23. So once again, you see that the most expensive thing going is the floating point divide. So you want to avoid that if at all possible, and use some other cheaper instruction to give you an equivalent result if at all possible. Similarly, you see that doing a plain old integer multiply on this particular CPU takes 3 clock pulses, and that's why we were using shifts, which take 1 clock pulse. They don't show it in the table, but an integer, a simple integer operation, which includes addition, subtraction, shifts, exclusive ORs, and that kind of stuff, right? Those are all 1 clock pulse operations. So that's why we were doing that shift as opposed to a real actual multiply, because it takes 1 cycle versus 3, right? So questions about what we mean by the latency, how long it takes to pump the thing through the circuit to get the result to pop out, how many clock pulses, and then the cycles per issue is how long do you have to wait to pipeline in the next pair of operands into the circuit. So another nasty thing about you'll notice about this divide stuff is it takes a long time and it's variable, but you also have to wait for the whole thing to finish before you can pump the next one in. It's not in any sense able to be pipelined. So the other kind of slightly weird one in this CPU here is the double precision floating point multiply takes either 4 or 5 cycles, but you can pipeline it. So it has a cycles per issue of 1. So the multiply is not near as bad as the divides are. The divides are the nasty ones, and they're not amenable to being pipelined. So a single or double precision floating point add you can think as taking the same amount of time as an integer multiply, right? So any questions about this? Okay. So somebody's got a question up here about the computers downstairs. I think you're referring to the 162, 164 labs, 165, or well, I guess the other one's 167. Um, all we said about those is those are Kaby Lake um, model processors. So they're newer than the ones, for example, in 405 or 418. I guess, I didn't show you how you get this information. But, um, so here's one of the ones downstairs. This is in lab 162 lab. And if you do the command ls CPU, it shows you what model the processor is. And if you look that up, that's a Kaby Lake processor, and I'll show you how you can see that. So if you go to here, you'll see that Core i7 7700K, which is the processor that's in those labs in 162, and 164, and I believe also 165. And 7 is a Kaby Lake processor, right? It came out in 2017, so they're relatively new. The ones in the 405 lab are these Skylake processors, so they're a couple years older. They're this model processor. And then the ones in the Linux pool are these guys. They're Sandy Bridge. So those are getting pretty long in the tooth now. They're almost 10 years old. And then Schofield is the one that came after the Sandy Bridge. He's an Ivy Bridge processor. So he's from around 8 years ago now. So that's the one, the when you're doing all your labs on is an Ivy Bridge. So it's real close to being exactly similar to a Haswell. It's the one right before the Haswell came out. And then the one in the um, 405 lab after the Haswell came out, and the ones downstairs are the Kaby Lakes, relatively. I don't remember what the ones in 420 are. I think they're one of these two. This is how many cores that are on that particular CPU, right? And so all of ours are going to be the 4-core i7 processors, except if you go to the cluster machines. Look at those are Xeons. So they have this particular model Xeon that we're using in there has 2 processor chips on the motherboard, and each processor has 6 cores in it, right? So you see, it says you got 6 cores per socket, and you got 2 sockets, 2 processors, and then it's hyper threaded, so you got 2 threads per core, so you get 24 threads that can run at the same time is what that's saying. So those are the ones in the cluster. In the clusters, you tend to use these processors with many more cores in them because it's high performance computing is what you're trying to do. And these machines also have gobs of memory on them compared to the lab machines that have 128 gigabytes of RAM, for God's sake, right? And the ones in the labs, like this guy, I think only has 16, but 16 is plenty, right? So those are the different types of computers that are in the department and how they relate to these different model numbers in the Intel models, right? So somebody's asking a question, why can't I pipeline the division? Well, that's what this is telling me here. The um, cycles per issue is saying, well, you'd have to wait till the whole thing finishes before you could issue the next one. So is that what you were asking? It's because of the cycles per issue. Or are you asking why you can't build the circuit in such a way that you could pipeline it? That's a long and more complicated answer than I can have time for now. But we'd have to look at the actual steps involved in doing the division and how the circuitry is used to do that, so that you're still using the circuitry that would be needed if you wanted to begin the operation on another one. So it's we'd have to get down to the gate level to explain to you why that is. Okay, but anyways, that's another course. So the homework, remember, is this guy. This is all in your text, right? And so your homework problems are saying, oh, if we were running on this particular CPU with the latency bounds from table 512, what would happen if I ran that inner product code through it? But for the purpose of the lecture today, we're talking about a NALM that has these properties, right? And what you need to remember is we only have one floating point multiply unit and one floating point add unit. We've got a couple of simple integer things and only one thing that can do a multiply or divide of an integer. So we can get a couple of simple integer things going. At the same time, we got one multiply of all these other things, right? And it's only got one load and one store path, whereas the Haswell you looked at had two load and store paths. And these, notice that loads and stores can be pipelined, right? So I could issue a load, and if I hit in the L1 Dcache that we explained in the next chapter, then that's going to take 4 cycles to get over into a register. But immediately after the first cycle, I could issue another request to load something. So I can pipeline those load requests, pulling things out of the cache as well. So you need to understand that, right? But it only has one load and one store data path to the memory, to the cache, whereas the Haswell has 2 paths for each of those independent paths. So we're getting down to a little more detail of how the computer actually works now, right? So we got this little combined benchmark thing we've been looking at, where we have a vector of a certain length and we factor in some particular kind of operation, and we run some tests to see how many cycles per element it takes to do. And we were getting numbers like this out of the combined 4. And remember that the combined 4, what he did is he had the temporary variable, the local variable that the compiler could figure out he could keep in a register and not have to touch memory. The operation walking across the vector, accumulating it into this register, and then we're dumping the register one time back to memory. And as well, we got rid of the little thing having to go to memory every time to get the length, and we went and grabbed it and chucked it in a local variable, so he presumably could keep that in a register too, not causing a memory reference every time we go through this cycle. So we got this for loop going, varying this I, and hopefully I could be left in a register, right? And you just keep incrementing it and comparing it to this thing in this other register. So you're eliminating all those memory references. That's why it's able to go fast. Because remember, touching memory is really going to slow you down. So being able to write your code in such a way where the compiler can see that he can use these local variables as just registers is going to make the thing go fast. So that's why we got the speed up that we're seeing in this table. The original one, nasty one, was like 28 or something, I think. And so then they're saying, well, what's the latency bound? And that's just how many clock pulses does it take to do that type of operation. Remember, the multiply was a 3-stage operation. You had 3 clock pulses. So that's the bound that you would look at with the latency, right? So we're kind of right at the bound with the way that we have the solution codified. But we can do better than the latency bound, right? Because we can arrange to pipeline things like we explained before. You could push one through and then immediately push another pair of operands through. But the reason that this is not beating the latency bound, taking advantage of the pipelining effect, is because there's a data dependency in our code. And to understand that, we have to, get a little down and dirty with how the thing is actually working. We have this identity, which if this was a multiply, the identity is set to 1, if you remember in the code. And then we multiply the thing times d0, and then we increment the thing, go through the loop, and then we grab the result of this and we multiply it by the element. And then when we get the result of that, we multiply it times the next element. So we're waiting at each step along the way. These are all the things that have to be done, right? We're waiting for the result of the previous one to finish before we can start the next one. So that is this latency of the 3 pulses of the clock that it takes to do that multiply. I have to sit here and wait, and then I can take my other operand and feed it into here with the result of that one, and then have 3 clock pulses. So this is a data dependency. I have to wait for the result of the previous operation before I can begin the next. Well, we can change the code to get rid of that data dependency in a lot of different ways. One way we can get rid of it is by unrolling the loop. And so this is sort of getting into what your homework problems are about, loop unrolling. So the first attempt at loop unrolling we'll look at is, well, let's just do twice as many operations per loop, and then we'll increment the loop counter by 2 rather than 1. And we'll have this thing that says, take the X, which is our temporary that we're accumulating into hopefully a register, right? And we'll take that piece of data, we'll do the operation on it with that thing, and then we'll get the result of that, and then we'll do this operation over here with the result of that. And anytime you unroll the loop, if you're jumping by 2, well, what if you have an odd number of things total to walk across? Well, then you'd have to do the last one there. So you always have, when you're loop unrolling, something that comes after the thing that takes care of whatever slop is left over. You know, if you unrolled it by 8, you might have as many as 7 things that you had to do that didn't get taken care of. So you always have that when you do the loop unrolling. So let's look at this. Notice we got X op di, and the result of that being multiplied and or added, whatever the op is, times the next one. So what did that do to the data dependencies? Well, if we run it and you unrolled it 2 ways, 2 per loop, right? We didn't improve anything in the add, but we cut the multiply in half, and we didn't get any improvement in the floating point stuff. So we dropped the multiply below the latency bound. So we would suspect that the reason that that's happening is what? We're getting some pipelining effect going with that multiply. And we know we only have one integer multiply unit on this particular NAILM CPU, right? So we must be getting some pipelining if we're getting 1.5 cycles per element, because the latency bound is 3. So the explanation has got to be it's pipeline somehow. So this is the association that we have in there, right? So somehow we got some pipelining going on with the multiply, but not if the operation was addition, right? So let's look at another example. We originally had this X op di, and then we had the op of di plus 1. Now we want to do what's called reassociation within the loop unrolling. So rather than doing the one on pair on the left first, why don't I do the pair on the right first and see what effect that, if any, might have on the outcome of how fast it could go, right? And then, of course, you got to finish your remaining stuff. Can this change the result of the computation? Well, remember that floating point numbers on the computer, as opposed to in the math book, are not associative. You might get a different result, right? Because of rounding and all that kind of nonsense, right? So, but what's to say one's any more valid than the other, on the other hand, right? So, yeah, it might produce a slightly different result doing the two on the right first as opposed to doing the ones on the left first and then the one on the right. But they're arguably equally as valid a result. But can we speed it up by doing the ones on the right first? Well, look at the table. When we did the reassociation of the unrolled loop, two-way unrolled, these all stayed the same for the integer stuff, but the floating point stuff now dropped down here to half of what it was before and went from 5 to 3 here. So we got below the latency bound on everything but the integer add, right? Because the latency bound is just one cycle on an integer add. So that looks like that had some effect, right? That reassociation of doing the pair on the right versus the pair on the left first. And then the question is, why in the world did that work faster than doing the ones on the left? And of course, the answer is going to be that we've broken yet another data dependency that existed in the code. And to understand this is a little complicated, but we got a pair of things that we pulled up out of memory, right? And we're pumping those into this three-stage multiply unit, say for a integer multiply, right? Or a floating point add is also a three-stage thing, either one, right? We're showing a multiply here. So say that's 3 pulses of the clock that it takes to get the result out. And then the result is going to be sitting here, and originally X is going to be our identity, 1 in the case of multiply. And we're going to take the X and multiply it times the result of those two things, right? But look at what's happening in the pipelining. While this 3 pulses of the clock is happening, right? What's the cycles per issue on this thing? It's 1, right? So if I had some other operands to feed into the multiply unit, after the first pulse of the clock, if I already had those operands, I'd be good to go and shove that into the multiply unit in a pipelined fashion so that this guy is now at stage 2, he's in stage 1, right? And if I had yet another pair of operands to do, this could be at stage 3, he could be at stage 2, and I could pump him in at the beginning at stage 1, right? And then when I get my result out here to do this multiply, now it's competing for the same unit, right? So it could be at stage 1. And these guys could be finishing up as this guy is doing his 3 stages, right? So I can get this overlap effect of these later guys being fed into the multiply unit because I have distinct pairs of operands. So I have removed yet another data dependency from doing it with the association on the left, where at every step, one of the operands was identical. It was the X. So I couldn't take advantage of my pipelining, right? I had a hidden data dependency in there. So that's why this one ends up running a little faster than the other one. Does anybody see anything screwy about the explanation I just gave? What does the code look like? In a loop, All right. And the loop is gonna, we don't aren't doing that. We're doing the reassociated one, right? And we're doing the loop unrolled business. There, no, that's not it. So we're doing the loop unrolled thing, right? And we're associating on the right. That's the one we're doing, right? So I got this I and this I plus one, and now I hit the bottom of the loop. What does the loop do? It adds two to this guy, I, which hopefully is in a register. Can I do that at the same time that this operation here is still in his 3 clock pulses? Yeah, because I got an independent unit that does the integer add from the integer multiply or whatever, right? So that can overlap with this. And then the result is actually going to be a branch, right, of whether I fall through or I branch around the thing because I'm through, right? So I have to do the compare for the branch, right? But then I could drop into here and pick up the next pair of operands to work on before the other one finished, possibly, right? But you say, wait a minute, that doesn't make any sense because he hasn't done the added into the accumulator part yet. Why would he start on the next pair there before he's done that addition there? So to get the effect, we've got to start this guy before this result comes out, which means we haven't done the thing on the left. So how are we doing that next pair? 0, 1, 2, 3. Why are we? How can we do it when we haven't even done the multiply into the other guy? Isn't this instruction to do that physically after the instruction to do this? And the answer is yes, it is. But there's another characteristic of the computer that we haven't told you about yet called out of order execution. Computers have been doing this since 1964, by the way. The CDC 6600 computer was capable of doing this in 1964. So the out of order execution amounts to you're feeding a bunch of instructions in a pipeline up to the CPU through a fetch, decode, execute cycle. And there's some circuitry that's looking at those instructions as they're bubbling up into the pipeline. And it's issuing the instructions onto functional units. It's sort of saying, okay, I'm assigning this instruction to go use these functional units and these registers, right? Well, the way the thing actually works is it doesn't have to do the operations in the exact order that you see them listed when you're looking at it in GDB or an object dump or something. If it can get the functional units more effectively utilized, either through pipelining or through superscalar separate units, it can issue instructions that are below where the true next instruction would be to go ahead and start working if it would compute the same result. And so it has circuitry that determines that, right? And so it can do an out of order issue on that opcode that's going to operate on those two operands, the the 2 and the 3, while the 0 and the 1 might even still be going through the functional unit, the 3-stage functional unit. It could have gone up through the loop, done the add, done the branch, fallen into the next instruction, and grabbed these two things and pumped them into the multiply unit before that other one actually even finished. And this instruction actually appeared first as you read it on the page, but it's going ahead and doing that instruction in an out of order issue to get the pipelining going, because it will compute the same result as if I waited for this one to finish here, right? So that's a very complicated device that we're describing how that works, right? That's maybe not what your off the bat conception of what the computer was. When you think about the operations being executed on the computer, you think about them happening in the exact sequence you see in the assembly language, right? And that's true in the sense that the result that gets computed has to be identical to doing them in that order. But when the CPU actually is executing the opcodes, it's not constrained to do them in that exact order. It can do them out of order as long as it produces the same result. And so it has to have some smart circuitry in there that can tell that, yeah, I can go ahead and issue this instruction while this one is still going before I've even done that one, even though that one physically was in memory sitting in front of this one, right? Several instructions in front of getting to that one because we got back to the top of the loop and everything, right? So that's this effect of out of order issue, getting the milking the superscalar speed up and the pipelining speed up for us. So that's pretty complicated to understand, right? But that's what you have to understand how the computer actually really works. And there's a bunch of other crud we haven't gotten to yet that's complicated too, that some other stuff that's going on. Okay. So do you see how it can get to those second pair of operands and actually get them into the multiply unit, possibly before the previous pair even finished? And so it would be overlapping probably with this one being pipelined into the thing. And so you get this overlap, and that's why you get those numbers, right? That's why you got this number with the reassociation cutting that in half and dropping that one from 5 to 3, right? The latency bound, how many pulses does it take to do a floating point multiply on this CPU is 5, but we're actually getting a result every 3 cycles because of the pipelining, right? And in the case that we're looking at here, the pipelining is happening because when we reassociated it, we removed a data dependency and allowed this thing to happen. Does that make any sense? It's getting a little deep, right? A little complicated to understand how the thing works, and it gets a little deeper still, so hang in there. So another thing we can do in addition to the reassociation, and this is what you'll see, is multiple accumulators. We can remove further data dependencies by having multiple accumulators. And so now I'm going to take the DI, multiply it times the accumulator X0 and the DI plus 1 and do that. And then when I get down and I'm completely finished with everything, I do the one operation to combine the two accumulators, right? So this is the normal sort of thing you see. And in your book, the terminology you have to learn is the loop unrolling two by two. This is a loop unrolling doing two things per loop, but it's got two accumulators. So that's a 2 by 2. And your homework problems are like 6 by 1 and 6 by 6 or something like that, right? So the first number is how many things you're doing per loop. How many times did you unroll the loop? How many ways? And the second number is how many accumulators are you using within the loop, right? So that's the terminology that they're using, right? So this is doing a 2 by 2. I got 2 accumulators. Will this go any faster than the other one? So I unrolled it 2 ways, and I had 2 accumulators going. We finally were able to get the integer add down to 1.5. And these guys all stayed the same, and the multiply dropped a little bit more down to 2.5. And that's because this is the analysis now, where we have each of these x0, x1 starts out at the identity value. You take d0 and d1. We only have one of these functional units. That shoot, you look like, you got two, but you only got one. But you're pumping this in, and you're pipelining that one in, right? And then you're pumping that one in, and you're pumping that one in. So you're pipelining all these things through the same functional unit, getting the overlap. And you get a lot more overlap when you removed having that dependency of the one single accumulator that you had, right? You got some overlap, but it was overlapping with putting the thing in the accumulator. Now we got a lot more degrees of freedom going on with the two accumulators, right? So these things can kind of overlap in a much nicer fashion, right? Than just doing the one accumulator. So when we get through, you got this one last operation that happens down at the bottom, right? So that's a little bit of a fudge factor in computing your numbers that has to combine the two accumulators, right? And that can't happen until both of the results show up. So he can't overlap with anything. He's just going to cost you the 3 cycles at the end after these guys have completely finished. So you see how we can change our code knowing how the CPU actually works, knowing that it's superscalar, knowing the number of which type of functional units we have, and how they can be used, and taking advantage of out of order issue and pipelining to get the thing to go through faster. So to really understand how to write your code so that it works fast, you have to have a very deep understanding of that specific CPU's characteristics. So once again, the homework one is this CPU, where you got this extra flexibility thing going now, where this functional unit and this functional unit have a collection of things they might be able to do, but you can only do one at a time. Think of it as one data path in, one data path out. And so but it gives you the flexibility of, if I wanted to do 4 integer things at a time, I could do it, right? I could do 2 integers and then 2 floating point additions at the same time. So this is the one that you're working on. The other thing you have to realize is when we were doing these pumping in the data things, you're saying, well, wait a minute, doesn't it take 4 cycles to go get that out of memory? Yeah, it takes 4 cycles, but it's also pipelined, right? Go back up here to this. See, the latency is 4 cycles to once I issue the request to get it out of memory. This is all assuming everything goes perfectly as good as possible and it's sitting right there in the top level cache. It takes 4 cycles, but I can issue another one right after it, right? So I can pipeline those things coming up out of memory as well as pipelining the adder or the multiplier, right? In your Haswell guy, you got 2 paths going to memory. So each one can be pipelined. They still take 4 is the latency, but you got 2 paths. So you can have 2 things going independently, pulling things out of that cache. And each of these can be pipelined. At the same time, you're storing two things, which can be pipelined, right? So we're learning more and more detail about how the CPU actually works, right? There's more to come. Questions about any of this crazy stuff? Well, I guess you noticed that the homework due date has been pushed back to Monday at 11:30, I think it is. So you can, if you still have stuff to work on your bomb, you can concentrate on that the rest of the day and get to your homework after you get that off your back. It's just that we didn't get to the discussion of some of this loop unrolling and multiple accumulators and how to think about the functional units until today. So I pushed the homework back to Monday. So office hours are 2 today. Got one thing due this evening and then one thing due Monday evening. A little bit different scenario. Questions about anything before we go? Well, I will see you Monday morning then. Have a great weekend. Happy defusing if you're still working on your bomb. Have a good weekend. Read the chapter on this. The chapter does a very good job of explaining this. It's really dense stuff that we've gotten to, so you need to go read word by word in the chapter and spend time on it. Talk to you later. Bye-bye.